We're going to take a look at doing iterations, finding approximations with the Runge-Kutta method. Now, if you saw my video on Euler's method, this method's going to be very similar, but it's going to be how we get those approximations is slightly different because we're going to do a weighted average of slopes. And I know it looks a little bit cumbersome, and we're going to talk through it a little bit, but this is how we're going to find our approximations. The important part is that you want to divide up the integral into little pieces of equal length. That length is going to be your step size h. And then the values of K1, K2, K3, and K4 are given by these formulas. You can see that they're very, very different, but unique, still the same. And then we can calculate our delta y, and then we'll finish up by doing our approximation by adding our initial value for y plus our delta y. Now, just like we did with Euler's method, I'm going to work through one of the iterations for a differential equations following these steps. So let's take a look at that. I'm going to find the approximations for this first derivative here. That is y prime equals x squared plus y squared. We're told the initial value y of 0 is 0, and we are told to use h step size of 0.1. So I'm going to get that started for us so that we can look at these iterations. So let's begin. We're going to say that y sub 0 plus 1, because we're going to let n equal 0 here, is going to be y sub 0 plus that delta y, okay? And this delta y is unique for Runge-Kutta method, so let's take a look at how we do that. That delta y is actually calculated by h times this Runge-Kutta weighted average. And that's of x sub 0, y sub 0, and h, meaning got to know all of those values. Okay, so how do we figure out what that is? Well, the first thing we got to know is that k sub 1 is your derivative. That's our derivative at, and I'm going to use this notation, at 0, 0 times h. Now, where did I get 0, 0? That's from my initial value that I was told here. Okay, now let's plug those into our derivative. We'll find that k sub 1 is 0 squared plus 0 squared, which is 0, times our h value, which is 0.1. And so I've got that k1 is 0. Okay, let's do k2 next. K2 is f of x plus h over 2. Y plus k over 2, I'm sorry, h over 2 times k1. Okay, so that means that k2 is the derivative at 0 plus 0.1 over 2, 0 plus 0.1 over 2 times 0. Okay, so k2 still then is the derivative at now 0.05 and 0. So now we can plug these into our derivative. That gives me 0.05 squared plus 0 squared. And that would give me 0.123, no. Sorry. I tried to do that in my head. 0.0025. There we go. And that's my K2 value. Okay, my K3 value now. Let me scoot up a little bit so we can see that. My K3 value is f of x sub 0 plus h over 2, y sub 0. Well, it looks like we lost track of my. Sorry about that. We lost our connection there with the document camera, but that's okay. We're working on K3, and we've got y sub 0 plus h over 2, and now we use K2 there. Okay. So we've got that K3 would be our derivative at 0 plus 0.1 over 2, and 0 plus 0.1 over 2 times the value we just found for K2, 0.0025. So essentially K3, we're finding the derivative at 0.05. And then this value, let's see, I did calculate that, 0.000125. And we're going to plug those into the derivative. This is for x, and this is for y. We end up getting our derivative to be, let's see, we're going to square both of those values, grab my calculator here. I thought I had already punched them in. I didn't. We're going to get a very small decimal. And we end up getting 0.0025. This value being squared gets even smaller. So you can see our approximations get closer and closer together. Okay, now we need one more, and that is our K4 value. So let's bump this up just a little bit. We're going to get that our K4 value is going to be our derivative, x sub 0 plus h over 2, y sub 0 plus h over 2, k sub 3. Okay. And you can see the repetitive nature here. And that's why a lot of times these methods of approximation lend themselves so nicely to Excel or even MATLAB. If you want to program to do that, you are welcome to do that. It's a lot of number crunching. That's why I'm only doing one by hand, just so you know. Um, and we end up getting the same value as before. Now, when you put that all together, okay, remember this has got to go back up here. When you put it all together, you've got that y sub 1, and I'm going to just draw an arrow to remember we're jumping. Now that we've got this, we've got that y sub 1 is y sub 0 plus h times this weighted average. Now, here's how the weighted average goes. It's K1 double K2 double K3 and then add K4. Okay, so let's plug in what we have. We've got 0 for y sub 0, h is 0.1, K1 was 0, K2 was 0.0025, K3 was the same, and then K4 we just added. And the only thing we forgot is that we need a 1/6 in front here. So that's a 0.1 times 1/6 times this weighted average. And the 1/6 is playing into the weighted average part because you've got 1, 2, 3, 4, 5, 6 items there, even though you've only got 4 with the multiplication. But that's how it's playing in. And let's get that value for our calculator. So plugging that in our calculator looks like y sub 1 is 0.002083. And again, you're using this weighted average for the Runge-Kutta method, that 1/6, and then you're having these weights of the K values, and then you can trace back in how we found the K values as well. Now, if you want to set up the rest of the problems in this assignment using Excel, I totally understand that. Please know that you are using step sizes here and you're only doing 2 iterations, okay, for each one of them, but there are 6 to work through. So if you have questions or comments, please let me know down below. I would love to hear if you chose to run the iterations in Excel or in MATLAB. And as always, thanks for watching.